Tonight, we're going to talk about something that sounds simple, but is actually one of the most confusing ideas in all of science. Spacetime. You've probably heard this word before. Scientists throw it around constantly. Einstein's theory of spacetime. The fabric of spacetime. Spacetime is curved, but here's what most people don't realize. When you actually dig into what spacetime means, when you try to understand what it really is, you discover something unsettling. We don't know. We use this idea every single day. Your GPS wouldn't work without it. We've photographed it being bent around black holes. We've detected ripples moving through it. And yet, we have no idea what it actually is. By the end of tonight, you're going to understand why this is one of the biggest unsolved mysteries in physics, and why solving it might change everything we know about the universe. Before we dive in, if you're interested in this kind of deep exploration, a quick like or subscribe really helps the channel grow. It makes a huge difference. Now, let's begin. Let's start in 1905. Albert Einstein was 26 years old, working as a patent clerk in Bern, Switzerland. He wasn't a professor. He didn't work at a university. He examined patent applications for electromagnetic devices during the day and thought about physics at night. And in that year, 1905, he published 4 papers that would change physics forever. One explained Brownian motion and proved atoms were real. One explained the photoelectric effect and helped establish quantum mechanics. And 2 papers introduced what we now call special relativity. Special relativity sounds complicated, but the core idea is actually straightforward. Einstein realized that the speed of light is always the same, no matter how fast you're moving. This seems impossible at first. If you're on a train moving at 100 kilometers per hour, or about 62 miles per hour, and you throw a ball forward at 20 kilometers per hour, or about 12 miles per hour, someone standing on the ground sees the ball moving at 120 kilometers per hour, or about 75 miles per hour. The speeds add up. That makes sense. That's what we expect. But Einstein showed that light doesn't work this way. If you're on a spaceship moving at half the speed of light, and you shine a flashlight forward, you might think the light would move at 1.5 times the speed of light from the perspective of someone watching you. But it doesn't. The light moves at exactly the speed of light, about 300,000 kilometers per second, or about 186,000 miles per second, both from your perspective and from the perspective of someone watching you from outside. The same speed. Always. This seems impossible. How can light be moving at the same speed for both observers when one observer is already moving at half the speed of light? Einstein's answer was radical. Space and time adjust to keep the speed of light constant. If you're moving very fast, time literally runs slower for you from the perspective of someone standing still. And distances in the direction you're moving actually contract. They shrink. These aren't optical illusions. They're real physical effects. Time and space are not absolute. They're relative, depending on your motion. The only thing that's absolute, that's the same for everyone, regardless of how they're moving, is the speed of light. This was shocking in 1905. It overturned centuries of assumptions about how the universe works. Newton had built physics on the idea that time flows the same for everyone, that a second is a second, no matter where you are or how fast you're moving. Einstein showed that wasn't true. Time is flexible. Space is flexible. They bend and stretch depending on your motion. Think about what this really means. If you could build a spaceship that travels at 99% of the speed of light, and you took a journey to a star 10 light years away and back, from your perspective on the ship, the journey might only take a couple of years. But when you returned to Earth, 20 years would have passed. Your friends would be 20 years older. Your children might now be older than you. This isn't science fiction. This is what Einstein's equations predict. And it's been confirmed by experiments countless times. We've tested this with particles in accelerators. Unstable particles that normally decay in microseconds live much longer when they're traveling at 99.9% of light speed. We've tested it with atomic clocks on airplanes. When you fly an atomic clock around the world and compare it to an identical clock that stayed on the ground, the traveling clock shows less time has passed. The difference is tiny. Just a few hundred nanoseconds, but it's measurable and it matches Einstein's predictions exactly. The implications are profound. There's no universal now. No cosmic clock ticking at the same rate everywhere. When you say something is happening right now on a distant planet, that statement has no absolute meaning. Different observers moving at different speeds would disagree about what right now means. They disagree about which events are simultaneous. Time is not a river flowing at a constant rate for everyone. It's more like a fabric that can stretch and compress depending on how you're moving through it. But Einstein wasn't done. Special relativity only dealt with objects moving at constant speeds. It didn't handle acceleration, it didn't handle gravity, and gravity was a problem. Newton's law of gravity had worked brilliantly for over 200 years. You could use it to predict the motion of planets, the trajectory of cannonballs, the orbits of moons. It was one of the most successful theories in the history of science. But Einstein realized it couldn't be right. Not completely. Newton's gravity worked instantly. If the sun suddenly disappeared, Earth would immediately fly off into space, according to Newton's equations. The gravitational pull would vanish instantly across 150 million kilometers, or about 93 million miles of empty space. But Einstein had just shown that nothing can travel faster than light. No signal, no force, no information can cross space instantly. If the sun disappeared, it would take about 8 minutes for the light to stop reaching Earth. That's how long light takes to travel from the sun to us. And Einstein realized gravity couldn't work any faster than light either. There had to be a delay. Something had to carry the gravitational force, and whatever it was, couldn't move faster than light. This led Einstein to one of the most productive thoughts of his life. He called it the happiest thought he ever had. It came to him in 1907. He was sitting in his office at the patent office, thinking about gravity, when he imagined a worker falling off a roof. While the worker is falling, Einstein realized the worker doesn't feel their own weight. They're weightless. They're in free fall. If they dropped a hammer while falling, the hammer would float next to them, falling at the same rate. They wouldn't see the hammer accelerate away or toward them. It would just hover there in mid-air from their perspective. This seems obvious now. We've all seen footage of astronauts floating in the International Space Station. But Einstein realized something profound. The worker falling off the roof and the astronaut floating in space are experiencing the same thing. They're both in free fall. The astronaut isn't actually floating in zero gravity. They're falling toward Earth, just like the worker. But they're also moving sideways, fast enough that they keep missing Earth. They're in orbit, continuously falling, but continuously missing the ground. And that's why they feel weightless. Not because there's no gravity, but because they're in freefall. Einstein realized that being in freefall is indistinguishable from being in empty space with no gravity at all. And being in a rocket accelerating upward is indistinguishable from standing on the surface of a planet feeling gravity pull you down. You can't tell the difference. If you're in a closed room with no windows, There's no experiment you can do to determine whether you're sitting on Earth's surface feeling 1 g of gravity or sitting in a rocket in deep space accelerating upward at 1 g. The effects are identical. This is called the equivalence principle. Acceleration and gravity are equivalent. They're the same thing. And this was the key insight that led Einstein to his theory of general relativity. If acceleration and gravity are the same thing, and if special relativity says that acceleration affects space and time, then gravity must also affect space and time. Gravity must curve space and time. It took Einstein another 8 years to work out the mathematics. From 1907 to 1915, he struggled with the equations. He learned advanced mathematics he'd never studied before. He made mistakes, published wrong results, corrected them, and tried again. It was the hardest work of his life. He later said the final year, from late 1914 to November 1915, was the most exhausting and demanding time of his entire career. But in November 1915, he finally got the equations right. He published his theory of general relativity, and physics would never be the same. General relativity says that mass and energy curve spacetime, and objects moving through curved spacetime follow curved paths. That's what we experience as gravity. It's not a force pulling objects together. It's objects following the straightest possible paths through this warped geometry. Those paths just happen to curve because the geometry itself is curved. The classic analogy is a rubber sheet. Imagine stretching a flat rubber sheet taut. If you place a heavy ball in the middle, it creates a dip, a curve in the sheet. Now, if you roll a smaller ball across the sheet, it will curve toward the heavy ball. Not because the heavy ball is pulling it, but because the sheet itself is curved. The small ball is trying to roll in a straight line, but the curved sheet forces it to follow a curved path. This is what mass does to spacetime. The Sun, with its enormous mass, curves spacetime around it. Earth is trying to move in a straight line through space. But the curved spacetime around the Sun forces Earth to follow a curved path. That curved path is Earth's orbit. We experience this as the Sun's gravity pulling on Earth. But from Einstein's perspective, there's no pull at all. There's just Earth moving through curved spacetime. Now, this rubber sheet analogy is helpful, but it's also misleading in some ways. The rubber sheet is a two-dimensional surface curving in three-dimensional space. But spacetime is four-dimensional, 3 dimensions of space plus 1 of time, and it's not curving in some higher dimensional space. It's curving in on itself. This is hard to visualize because we can't picture 4-dimensional geometry. Our brains evolved to understand 3 spatial dimensions, not 4-dimensional space-time. Also, the rubber sheet analogy makes it look like gravity is pulling the balls down. But that's our Earth gravity doing the pulling in the analogy. In real space-time, there's no external force. The curvature itself is gravity. Objects follow geodesics, which are the straightest possible paths through curved spacetime. A planet orbiting a star is following a geodesic. It's moving in what it thinks is a straight line, but because spacetime is curved, that straight line curves back on itself, creating an orbit. Einstein struggled for years to find the right mathematical language to express these ideas. He needed tensor calculus, a branch of mathematics that deals with objects that have multiple indices and transform in specific ways when you change coordinate systems. He'd never studied this in detail during his university education. He had to learn it from his mathematician friend Marcel Grossman. Together, they worked through the mathematics, trying different formulations, making mistakes, publishing preliminary versions that turned out to be wrong. At one point, Einstein thought he had the right equations, published them, then realized they didn't reduce to Newton's law of gravity in the appropriate limit. That should have been a red flag. Any new theory of gravity has to match Newton's predictions when gravitational fields are weak and objects are moving slowly, because Newton's theory works perfectly well in those situations. Einstein's preliminary equations didn't do this. So he went back to the drawing board. The breakthrough came in November 1915. Einstein was in Berlin, working feverishly on the equations. He gave a series of lectures at the Prussian Academy of Sciences, presenting his progress week by week as he refined the theory. On November 25, 1915, he presented the final form of the field equations. These 10 interrelated equations describe how the curvature of spacetime is determined by the distribution of mass and energy. They're beautiful in their symmetry and elegance. They can be written compactly as G equals 8 pi t, where G is the Einstein tensor describing the curvature of spacetime, and T is the stress-energy tensor describing the distribution of mass, energy, momentum, and pressure. These equations are deceptively simple-looking, but solving them for realistic situations is extraordinarily difficult. They're nonlinear partial differential equations. The curvature affects how mass and energy behave, but mass and energy also affect the curvature, creating a feedback loop that makes the equations very hard to solve. For most realistic scenarios, you can't solve them exactly. You need numerical simulations run on powerful computers. Even today, with all our computational power, solving Einstein's equations for complex situations like two black holes colliding requires massive supercomputers running for weeks or months. This was a beautiful idea. It was elegant. It explained everything Newton's gravity explained, but in a more fundamental way. And it made new predictions that Newton's theory couldn't account for. One of the first successes was explaining the orbit of Mercury. Mercury, the closest planet to the Sun, has an orbit that's slightly off from what Newton's equations predict. The point where Mercury is closest to the Sun shifts very slightly with each orbit. This is called the precession of Mercury's perihelion. Astronomers had known about this for decades and couldn't explain it. Some thought there might be another planet closer to the Sun than Mercury, pulling on it and causing the shift. But Einstein's equations predicted the exact amount of precession without needing any extra planets. Spacetime was curved more strongly near the Sun, and that extra curvature explained Mercury's strange orbit perfectly. But the real test came in 1919. Einstein's theory predicted that light would be bent by gravity. More specifically, starlight passing near the Sun would be bent by the Sun's curved spacetime. The stars would appear to shift position slightly when the Sun was nearby. But you can't normally see stars near the Sunday. The Sun is too bright. It drowns out the starlight. You can only see stars near the Sun during a total solar eclipse when the Moon blocks the Sun's light. On May 29th, 1919, there was a total solar eclipse. Two expeditions, one led by Arthur Eddington, traveling to the island of Principe off the coast of West Africa, and another traveling to Sobral in Brazil, photographed stars during the eclipse. They measured the positions of stars near the Sun and compared them to the positions of the same stars photographed at night when the Sun wasn't nearby. The stars had shifted. Light had been bent by the Sun's gravity, exactly as Einstein predicted. The measurements matched Einstein's equations. When the results were announced in November 1919, Einstein became an overnight celebrity. Newspapers around the world ran headlines about the eclipse results. Einstein's face appeared on magazine covers. He was invited to give lectures everywhere. He went from being a respected physicist to being the most famous scientist in the world. By 1922, everyone in the physics community agreed Einstein had solved gravity. The problem was closed. The theory was complete, except it wasn't. Einstein's equations were beautiful, but they were also difficult to work with. They're a set of 10 interrelated equations involving tensors, which are mathematical objects that describe how space-time curves in response to mass and energy. Most physicists in the 1920s and 30s couldn't solve these equations, except in very simple cases. One of the simplest solutions was found by Carl Schwarzschild in 1916, just a few months after Einstein published his theory. Schwarzschild was a German physicist serving in the German army during World War I. Despite being on the Russian front, dealing with the harsh conditions of warfare in 1916, he found time to work on Einstein's equations. He solved them for the simplest possible case, a perfectly spherical, non-rotating mass sitting alone in empty space. The solution worked. It described how space-time curves around a star or planet. But Schwarzschild noticed something strange in the mathematics. At a certain distance from the center of the mass, the equations seemed to break. They gave infinite values. They stopped making sense. This distance became known as the Schwarzschild radius. For the Sun, the Schwarzschild radius is about 3 kilometers, or about 1.9 miles. For Earth, it's about 9 millimeters, or about 0.35 inches. These numbers seemed meaningless at the time because the Sun is much larger than 3 kilometers across. It has a radius of about 700,000 kilometers, or about 435,000 miles. Earth is much larger than 9 millimeters. It has a radius of about 6,370 kilometers, or about 3,960 miles. The strange behavior in the equations only appeared deep inside the physical mass, where the vacuum solution didn't really apply anyway. You can't use the vacuum solution for space-time inside a ball of matter, so most physicists ignored it. It was just a mathematical quirk, an artifact of the idealized spherical solution, nothing to worry about. Schwarzschild himself died just a few months after publishing his solution. He contracted an autoimmune disease while serving on the Eastern Front and died in May 1916 at the age of 42. He never knew how important his solution would become. For decades, the Schwarzschild radius remained a mathematical curiosity. Physicists knew about it, but didn't think it had any physical significance. Einstein certainly wasn't worried. In fact, he actively disliked the implications. If you somehow compressed a mass smaller than its Schwarzschild radius, the equations predicted something bizarre. Space-time would curve so strongly that nothing could escape, not even light. The object would become what we now call a black hole. And at the very center, all the mass would collapse to an infinitely small point, a singularity, where the curvature of space-time became infinite and the laws of physics broke down completely. Einstein thought this was absurd. He believed it revealed a limitation of the theory, not a prediction about reality. He wrote papers in the 1930s arguing that nature would never allow such a thing to happen. He believed that matter would resist being compressed that much. There would be some force, some pressure, some quantum effect that would prevent collapse beyond the Schwarzschild radius. The singularity was a mathematical artifact, not a real physical possibility. It was like dividing by zero in an equation. You get infinity, but that doesn't mean infinity exists in nature. It means you've pushed the equation beyond its domain of validity. Most physicists agreed with Einstein. The idea of a star collapsing so completely that it disappeared from the universe seemed ridiculous. Stars are held up by pressure. Hot gas pushes outward. This pressure balances gravity's inward pull. When a star runs out of fuel, It cools down, pressure drops, and gravity takes over. But surely there would be some force that would stop the collapse. Maybe the pressure of electrons pushing against each other, a quantum effect called degeneracy pressure. This is what holds up white dwarf stars. Or maybe the pressure from neutrons, which holds up neutron stars. Something would stop the collapse. It had to. But in 1939, J. Robert Oppenheimer, who would later lead the Manhattan Project, and his student Hartland Snyder published a paper that changed everything. They modeled a massive star running out of fuel, no longer able to support itself against its own gravity. They showed mathematically that for their idealized model, there was nothing that could stop the collapse. No pressure, no force was strong enough to halt it once it started. The star would shrink past its Schwarzschild radius and keep shrinking until it became a singularity, a point of infinite density where Einstein's equations themselves broke down. Later work showed this wasn't just true for idealized models. Even with realistic equations of state describing how matter behaves under extreme pressure, massive enough stars would still collapse completely. There's a mass limit, beyond which no known force can prevent collapse to a black hole. Oppenheimer and Snyder didn't call it a black hole. That term wouldn't be coined until 1967 by John Wheeler. They just described the mathematics of gravitational collapse. But the implications were clear. Einstein's own equations predicted that stars could collapse into objects from which not even light could escape. Objects where space-time became so warped that it essentially sealed itself off from the rest of the universe. Einstein hated this result. He thought it showed that general relativity must be incomplete, that something was missing from the theory. But he couldn't find a flaw in Oppenheimer's mathematics. The equations were correct. General relativity really did predict these objects. Einstein died in 1955, never accepting that black holes were real. For the next couple of decades, most physicists remained skeptical. Black holes seemed too strange, too extreme. They violated our intuitions about how the universe should work, but observations started to pile up. In the 1960s, astronomers discovered quasars, incredibly bright objects in distant galaxies that were pouring out enormous amounts of energy from very small regions of space. The only explanation that made sense was that these were supermassive black holes, millions or billions of times the mass of the Sun, feeding on gas and dust. The material falling into the black hole would heat up to millions of degrees and radiate energy before crossing the point of no return. And theorists were making progress understanding what black holes really meant for physics. In 1965, Roger Penrose proved a remarkable theorem. He showed that once a star collapses past a certain point, the formation of a singularity is mathematically unavoidable. It's not a matter of the star being perfectly spherical or having special properties. Any collapsing star would form a singularity. The laws of physics, as described by general relativity, literally forced it to happen. Stephen Hawking extended this work. In the late 1960s and early 1970s, working with Penrose and others, he proved that singularities are generic features of general relativity. They don't just appear in black holes. The Big Bang itself, the beginning of the universe, was a singularity, a point of infinite density and infinite curvature where time itself began. Hawking showed that if you run the expansion of the universe backward in time, using Einstein's equations, you inevitably reach a singularity. There's no way to avoid it within the framework of general relativity. This was deeply troubling. General relativity had been incredibly successful at describing gravity, space-time, and the motion of objects from planets to galaxies. But the theory itself predicted places where it broke down, places where the equations gave infinite answers and stopped making sense. Singularities were like signs posted in the mathematics saying, "Beyond this point, physics doesn't work." Then in 1974, Hawking made another discovery that shocked the physics community. He showed that black holes aren't completely black. They emit radiation. This became known as Hawking radiation, and it came from combining general relativity with quantum mechanics in a very specific way. Here's how it works. Quantum mechanics says that empty space isn't really empty. It's filled with quantum fluctuations, pairs of particles and antiparticles that pop into existence for incredibly brief moments before annihilating each other. This happens everywhere, all the time. In normal space, far from any black holes, these fluctuations are called virtual particles. They exist for such a short time that they can't be observed directly. They borrow energy from the vacuum, exist for a moment, then pay it back by annihilating. The uncertainty principle in quantum mechanics allows this to happen as long as it happens fast enough. The energy of these virtual particles and the time they exist are related by Heisenberg's uncertainty principle. The more energy they borrow, the shorter their lifetime must be. For typical virtual particle pairs, they exist for about 10 to the minus 23 seconds before annihilating. That's an incredibly short time. 23 orders of magnitude smaller than a second. But they're real in the sense that they have measurable effects. They cause tiny shifts in atomic energy levels that have been measured to extraordinary precision. Usually, these particle pairs appear and disappear so quickly that they don't have any observable effect on anything large scale. But near the event horizon of a black hole, something different can happen. The event horizon is the point of no return. Once something crosses it, that something cannot escape. The gravitational pull becomes so strong that you'd need to travel faster than light to escape, and nothing can travel faster than light. So, anything that crosses the event horizon is trapped forever, doomed to fall into the singularity at the center. Now imagine a virtual particle pair appears right at the edge of the event horizon. One particle appears just inside the horizon, the other just outside. Normally, they'd annihilate each other almost instantly. But in this case, the particle inside the horizon gets pulled in by the black hole's gravity before it can annihilate its partner. The particle outside the horizon escapes. To an outside observer, it looks like the black hole emitted a particle. But where did the energy for this real particle come from? It came from the black hole itself. When one particle of the virtual pair falls into the black hole, it has negative energy from the perspective of an outside observer. This is a strange consequence of general relativity near a black hole. The particle falling in reduces the mass of the black hole very slightly. The escaping particle carries away positive energy. The total energy is conserved, but the black hole has lost mass. Over time, this process causes the black hole to lose mass. It's slowly evaporating. The rate of evaporation depends on the size of the black hole. Smaller black holes evaporate faster. This is because the Hawking radiation temperature is inversely proportional to the mass. A black hole with the mass of the Sun would have a temperature of about 60 nanokelvins, that's 60 billionths of a degree above absolute zero. At that temperature, it would take about 10 to the 67 years to evaporate completely. That's incomprehensibly long. The current age of the universe is only about 10 to the 10 years, 13.8 billion years. A solar mass black hole would take 10 to the 57 times the current age of the universe to evaporate. But a smaller black hole would evaporate much faster. A black hole with the mass of a mountain, about 1 billion metric tons, or about 2.2 trillion pounds, would have a temperature of about 100 billion kelvins and would evaporate in a fraction of a second, exploding in a burst of high-energy radiation. Tiny black holes, if they exist, would evaporate almost instantly, releasing tremendous amounts of energy. This was revolutionary. It meant black holes aren't eternal. They have a finite lifetime. They would eventually disappear completely, evaporating away into radiation. And this created a new problem, one that has haunted physics for 50 years. It's called the information paradox. Think about it like this. Imagine you write a book, a detailed record of information, and then you throw it into a black hole. The book crosses the event horizon and falls toward the singularity. From the outside, the book is gone. All you can observe about the black hole is its mass, its spin, and its electric charge. You can't tell what fell in. A book, a rock, a star, it doesn't matter. The black hole looks the same regardless. In the 1970s, John Wheeler summarized this by saying, "Black holes have no hair, meaning they have no features that distinguish what went into them." Now, if black holes were eternal, you might say the information is still there, locked inside the black hole forever, inaccessible but not destroyed. But Hawking radiation changes that. The black hole evaporates. Eventually, it disappears completely, replaced by a cloud of thermal radiation. Thermal radiation is random. It doesn't carry information about what created it. It's like the heat from a fire. You can't look at the heat and figure out what was burned. This means the information about the book is destroyed. The words, the ideas, the specific arrangement of particles that made up the book, all of it is gone. This violates a fundamental principle of quantum mechanics called unitarity. Quantum mechanics says that information is never destroyed. It can be scrambled, spread out, hidden in incredibly complex ways, but it's always there in principle. If you knew the quantum state of every particle perfectly, you could reconstruct the past or predict the future with perfect accuracy. Information is conserved. But Hawking radiation seemed to destroy information. The quantum state of the book is lost forever. It's as if the book was erased from the history of the universe. This created a deep conflict between general relativity and quantum mechanics. One of them had to be wrong, or our understanding of both had to be incomplete. Physicists debated this for decades. Hawking initially argued that information really is destroyed in black holes, that quantum mechanics breaks down in extreme gravitational fields. Others argued that information must be preserved somehow, that we just don't understand the mechanism yet. The paradox remained unsolved, and it became a signal that something was fundamentally wrong with our understanding of spacetime. Einstein's beautiful theory of curved spacetime now predicted places where physics literally stops making sense. Singularities where the equations break down. Black holes that might destroy information. The theory was spectacularly successful in describing gravity and predicting phenomena from the bending of starlight to the existence of gravitational waves. But it also contained the seeds of its own destruction. It predicted situations where it couldn't be trusted, where a deeper theory was needed. Before we go any further into the mystery, let's pause and appreciate something remarkable. This idea we don't fully understand, this theory that breaks down at singularities and might destroy information, is something we use every single day. General relativity isn't just an abstract theory for understanding black holes and the Big Bang. It affects your life in concrete, practical ways. Let's start with the most obvious example. GPS. Your phone, your car's navigation system, any device that tells you where you are, uses a network of satellites orbiting Earth about 20,000 kilometers up, or about 12,400 miles. These satellites constantly broadcast signals containing the exact time according to atomic clocks on board and information about their positions. Your GPS device receives signals from at least 4 satellites, measures how long the signals took to arrive, and uses that information to calculate your position. The speed of light is constant. If you know how long a signal took to arrive and you know it traveled at the speed of light, you can calculate how far away the satellite was when it sent the signal. With signals from 4 satellites, you can pinpoint your position in 3-dimensional space. It's simple geometry. But there's a problem. The atomic clocks on the satellites don't tick at the same rate as clocks on the ground. There are 2 effects from general relativity at work here. First, the satellites are moving at about 14,000 kilometers per hour, or about 8,700 miles per hour, relative to the ground. According to special relativity, time runs slower for moving objects. From the perspective of someone on the ground, the satellite clocks should be ticking slightly slower. This is called time dilation due to velocity. The effect is tiny, but measurable. The satellite clocks lose about 7 microseconds per day compared to clocks on the ground. But there's a second effect that's even larger. The satellites are higher up in Earth's gravitational field. They're farther from Earth's center of mass, so they experience weaker gravity. According to general relativity, time runs faster in weaker gravitational fields. From the perspective of someone on the ground, the satellite clocks should be ticking slightly faster. This is called gravitational time dilation. The satellite clocks gain about 45 microseconds per day compared to clocks on the ground. When you add these 2 effects together, the satellite clocks run about 38 microseconds per day faster than clocks on the ground. That doesn't sound like much. 38 microseconds. But light travels about 300 meters, or about 984 feet, in 1 microsecond. If the GPS system didn't correct for these relativistic effects, your position would be off by about 11 kilometers per day, or about 7 miles. Within hours, GPS would be completely useless. Your navigation would tell you you're in the wrong city. The engineers who designed GPS knew this. They programmed the satellite clocks to tick at a slightly different rate to compensate for relativity. Every GPS calculation accounts for the curvature of space-time around Earth. Every time you use GPS to navigate, you're relying on Einstein's equations. You're using general relativity. And it works. It works perfectly. But do we understand what space-time actually is? No, we don't. We just know how to calculate its effects. Here's another example that's even stranger: gold. The metal gold has a distinctive yellow color. It's the only metal that looks yellow. Silver is silvery white. Copper is reddish. Iron is gray. But gold is yellow. Why? The answer involves relativity. Atoms absorb and emit light at specific frequencies depending on the energy levels of their electrons. For most metals, the frequency of light they absorb is in the ultraviolet range, higher energy than visible light. So, they reflect all visible light and appear silvery or gray. But gold is different. Gold atoms are heavy. They have 79 protons in the nucleus, creating a strong electric field. The innermost electrons are moving very fast in this strong field, fast enough that relativistic effects become important. According to special relativity, as electrons move faster, their mass effectively increases. This changes the spacing between energy levels in the atom. For gold, this relativistic effect shifts the energy levels enough that gold absorbs blue light instead of ultraviolet. When white light hits gold, the blue frequencies are absorbed, and the remaining light that's reflected is yellow, The color of gold is a relativistic effect. Without special relativity, gold would look silvery like most other metals. The same thing happens with mercury. Mercury is the only metal that's liquid at room temperature. Why? Again, relativity. Mercury atoms have 80 protons, and the innermost electrons are moving so fast that relativistic effects make the bonds between mercury atoms weaker than they would otherwise be. The atoms don't stick together as strongly, so mercury melts at a much lower temperature than you'd expect. Without relativity, mercury would be a solid at room temperature, and thermometers would work very differently. These aren't just curiosities. These are real, measurable effects of relativity in everyday materials. The universe we live in, the properties of the elements around us, are shaped by the curvature of space-time and the flexibility of time. And we use these effects without thinking about them. Here's another one. The entire internet. Well, not the entire internet, but a significant part of it. Fiber optic cables carry data as pulses of light. The timing of these pulses is incredibly precise. For long-distance fiber optic communication, especially for things like financial transactions where microseconds matter, engineers have to account for relativistic effects. Cables at different altitudes experience slightly different gravitational time dilation. The difference is tiny, but in high-speed networks transmitting billions of bits per second, even tiny timing errors add up. Corrections based on general relativity are built into the synchronization systems. Even more impressive is LIGO, the Laser Interferometer Gravitational Wave Observatory. LIGO is designed to detect gravitational waves, ripples in spacetime caused by violent cosmic events like colliding black holes or neutron stars. These ripples stretch and squeeze space as they pass through. The effect is incredibly small. When a gravitational wave passes through Earth, it might change the distance between 2 points separated by 4 kilometers, or about 2.5 miles, by less than 1/10,000th the width of a proton. Let me put that in perspective. A proton is about 10 to the minus 15 meters across. 1/10,000th of that is 10 to the minus 19 meters. The LIGO detectors can measure changes in distance that small. To give you a sense of scale, if the distance between Earth and the nearest star, Proxima Centauri, about 40 trillion kilometers, or about 25 trillion miles, changed by the width of a human hair, about 1/10 of a millimeter, or about 4/1000ths of an inch, LIGO would be able to detect it. LIGO detects this by splitting a laser beam, sending the two halves down perpendicular tunnels 4 kilometers, or about 2.5 miles long, bouncing them off mirrors at the ends and recombining them. If a gravitational wave passes through while the light is traveling, one arm of the detector will be stretched slightly while the other is squeezed slightly. This creates a tiny change in the time it takes light to travel down each arm, and when the beams recombine, they create an interference pattern that reveals the passing wave. The interference pattern changes because the light waves are slightly out of phase after one arm was stretched and the other squeezed. The first detection happened on September 14th, 2015. It was the first day of LIGO's first science run after a major upgrade. The signal arrived at the detector in Louisiana at 5:51 a.m. Central Daylight Time. 7 milliseconds later, it arrived at the detector in Washington State. The signal lasted about 1/5 of a second, starting at a frequency of about 35 Hz and rising quickly to about 250 Hz before cutting off abruptly. This pattern is exactly what you'd expect from two black holes spiraling into each other and merging. The analysis showed that the two black holes each had about 30 times the mass of the Sun. They'd been orbiting each other for billions of years, gradually spiraling inward as they lost energy to gravitational waves. In the final fraction of a second, they were orbiting each other hundreds of times per second, moving at significant fractions of the speed of light. When they merged, the collision released more energy in a fraction of a second than all the stars in the observable universe emit in the same time. About 3 solar masses worth of energy, the equivalent of annihilating 3 suns and converting all their mass directly to energy, was radiated away as gravitational waves in less than a second. That energy radiated outward at the speed of light as ripples in spacetime. The event happened 1.3 billion light-years away, so the waves took 1.3 billion years to reach Earth. When they arrived, they stretched and squeezed the 4-kilometer arms of LIGO by about 1,000th the width of a proton, and LIGO detected it. The discovery was announced on February 11, 2016, after months of careful analysis to make sure the signal was real and not some instrumental artifact or noise. It was front-page news around the world. It confirmed a major prediction of general relativity that had never been directly tested. Einstein's equations predict that accelerating masses create ripples in spacetime that travel at the speed of light. We'd seen indirect evidence before. Pulsars, rapidly spinning neutron stars, lose energy at exactly the rate you'd expect if they're emitting gravitational waves. But LIGO was the first direct detection. We'd actually caught the waves passing through Earth. Since then, LIGO and its sister observatories, Virgo in Italy and Kagra in Japan, have detected dozens of gravitational wave events. Most are from merging black holes. Some are from merging neutron stars. Each detection teaches us something new about these extreme objects and about the nature of gravity itself. The black hole mergers have revealed a surprising population of intermediate mass black holes, objects with masses between 30 and 100 times the Sun's mass. Before LIGO, we knew about stellar mass black holes formed from individual stars, typically 5 to 20 solar masses. And we knew about supermassive black holes in galaxy centers, millions to billions of solar masses. But the gap between was mysterious. LIGO found that gap is filled with black holes, suggesting formation mechanisms we hadn't fully understood. We've also learned about black hole spins. When 2 black holes merge, they're often spinning. Sometimes their spins are aligned with each other, sometimes misaligned. This tells us about how the black holes formed. Binary black holes that formed together from a pair of stars should have aligned spins. Black holes that formed separately and later captured each other gravitationally should have random spin orientations. The LIGO data shows both types exist. In August 2017, LIGO and Virgo detected gravitational waves from 2 neutron stars merging about 130 million light-years away. This event was special because neutron star mergers also produce light. Unlike black holes, which are dark, neutron stars are made of normal matter, and they glow. When they merge, they create a bright explosion called a kilonova. Within seconds of the gravitational wave detection, LIGO sent out alerts to astronomers around the world. Telescopes swung into action, searching the region of sky where the signal came from. Within hours, they found it. A new bright source in a galaxy called NGC 4993. Over the following days and weeks, dozens of telescopes observed the kilonova at different wavelengths from gamma rays to radio waves. It was the first time humanity had observed a cosmic event with both gravitational waves and light. It was the dawn of multi-messenger astronomy. The observations confirmed something physicists had long suspected. Heavy elements like gold, platinum, and uranium are created in neutron star mergers. The collision creates conditions so extreme that atomic nuclei are smashed together and rebuilt into heavy elements. The kilonova ejected about 1/100th of a solar mass of material. much of it gold and platinum. All the gold on Earth, every gold ring, every gold coin, every gold bar in bank vaults was created in neutron star mergers billions of years ago before the solar system formed. The gold was scattered into space, mixed with gas and dust, and eventually incorporated into the disk of material that formed the sun and planets. When you wear a gold ring, you're wearing atoms that were forged in the collision of neutron stars. Each gravitational wave detection is direct evidence that space-time is real, that it can be bent and rippled, that Einstein was right. We're not just inferring the existence of space-time from theoretical arguments, we're measuring it directly. We're watching it wiggle. But detecting gravitational waves doesn't tell us what space-time is made of. It just confirms that it exists and that it behaves the way Einstein's equations say it should. It's like detecting sound waves, traveling through air. You can measure the waves, study their properties, use them to communicate and make music. But measuring sound waves doesn't tell you what air is made of. You need other experiments to discover molecules and atoms. Similarly, measuring gravitational waves tells us spacetime can vibrate, but it doesn't tell us what the fabric doing the vibrating actually is. That remains a mystery. And then there are the black hole photographs. In April 2019, the Event Horizon Telescope collaboration released the first image of a black hole. It wasn't a photograph in the traditional sense. It was radio telescope data from observatories all around the world, combined using a technique called very long baseline interferometry. 8 radio telescopes spread across the planet, from Hawaii to Antarctica, from Spain to Chile, all pointed at the same target at the same time. They recorded radio waves at a wavelength of 1.3 millimeters, or about 0.05 inches, a frequency where the gas around black holes glows brightly. The technique works by combining the signals from all the telescopes as if they were parts of a single telescope the size of the Earth. The resolution you can achieve with a telescope depends on its size. Larger telescopes can see finer details. By spreading telescopes across the planet and combining their signals, you can achieve a resolution equivalent to a telescope about 13,000 kilometers or about 8,000 miles across. That's enough resolution to read a newspaper in New York from a cafe in Paris, or to see an orange sitting on the surface of the moon. But the process is incredibly difficult. You need atomic clocks at each telescope to precisely timestamp when each signal arrives. You need to record petabytes of data, so much that it couldn't be sent over the internet. Hard drives had to be physically shipped to a central facility for processing. You need to correct for Earth's rotation, for atmospheric effects, for the motion of the telescopes. And you need to do all this for signals coming from billions or trillions of kilometers away, so faint they're almost lost in noise. The result was an image showing a ring of light around a dark circle. The black hole was in the center of the galaxy Messier 87, about 55 million light-years away. The black hole itself is about 6.5 billion times the mass of the Sun. The dark region in the center of the image, the shadow, has a diameter of about 40 billion kilometers, or about 25 billion miles. That's about 3 times the size of Pluto's orbit around the Sun, and it's completely dark because it's the event horizon. No light escapes from inside. The ring of light around the shadow is gas orbiting the black hole at speeds approaching the speed of light. The gas is heated to billions of degrees by friction and magnetic fields. It glows in X-rays, visible light, and radio waves. The light we see in the image has been bent by the extreme curvature of space-time around the black hole. Some photons orbit the black hole multiple times before escaping. Some are bent just enough to reach our telescopes. The ring appears brighter on one side because the gas is rotating. On one side, it's moving toward us, and relativistic effects make it appear brighter. On the other side, it's moving away, and it appears dimmer. What you're seeing in that image is not the black hole itself. The black hole is the dark circle in the center, the region from which no light escapes. What you're seeing is the effect of the black hole on space-time around it. The light from hot gas is being bent, twisted, focused by curved space-time. The image is a direct photograph of Einstein's predictions. The size of the shadow, the shape of the ring, the brightness distribution, all of it matches computer simulations based on general relativity. In May 2022, the collaboration released an image of a second black hole, this one at the center of our own galaxy, Sagittarius A star. It's about 4 million times the mass of the Sun, much smaller than the Messier 87 black hole, but it's much closer, only about 27,000 light-years away instead of 55 million. Again, the image shows a ring of light around darkness. You're looking at curved space-time. You're seeing photons that have been bent by gravity on their journey to Earth. These images required some of the most sophisticated data processing ever done in astronomy. The raw data from the telescopes doesn't directly show an image. It shows correlations between signals at different telescopes. To turn this into an image, you need to run algorithms that essentially solve an inverse problem. Given these correlations, what image would produce them? There are many possible images that could fit the data. So the algorithms include assumptions about what images are likely based on physics and prior knowledge. The final image is the one that best fits the data while satisfying physical constraints. The amazing thing is that different teams using different algorithms and different assumptions all produced very similar images. The ring is real. The shadow is real. You're looking at light being bent by gravity. These images are literal photographs of Einstein's predictions made visible. They're not artists' interpretations or computer simulations. They're images constructed from real data. Photons that traveled from the edge of an event horizon across millions or tens of thousands of light years to reach Earth. We use this idea every single day in GPS, in the color of gold, in the liquidity of mercury, in fiber optic networks, in gravitational wave detectors, in photographs of black holes. We've built entire technologies on Einstein's framework, and that's both amazing and unsettling. It's like discovering that your house rests on an invisible foundation. You can measure how it responds to weight. You can calculate how it bends under stress. You can predict how it will behave, but the material itself remains unknown. So let's dig into the mystery. What exactly don't we understand about space-time? The answer isn't simple, but it can be broken down into three big questions. Three places where our knowledge hits a wall. Three puzzles that, if we could solve them, would revolutionize physics and possibly technology. What is space-time made of? Let's start with the most basic question. What is space-time? Einstein's equations describe how space-time curves in response to mass and energy. They tell us how to calculate the curvature given a distribution of matter. They predict how objects move through curved space-time, but they don't tell us what space-time actually is. In Einstein's theory, space-time is treated as a smooth continuum. You can zoom in on any point in space, and there's always more space at smaller scales. You can divide time into smaller and smaller intervals, and there's always more time. Space and time are continuous, infinitely divisible. This works perfectly for calculations at the scales we can observe. But there's reason to believe this can't be the whole story. Quantum mechanics, the theory that describes the behavior of particles at very small scales, says that almost everything in nature is discrete, quantized, coming in chunks rather than being continuous. Energy comes in chunks called quanta. Light comes in chunks called photons. Even the spin of an electron comes in discrete values. You can't have half a photon or an electron spinning at an arbitrary angle. The quantum world is fundamentally grainy, not smooth. This suggests that space and time might also be quantized at very small scales. There might be a smallest possible length, a quantum of space. There might be a smallest possible duration, a quantum of time. Below these scales, it doesn't make sense to talk about smaller distances or shorter times. Space and time would be fundamentally discrete, like a digital photograph made of pixels rather than a continuous analog image. This scale is called the Planck length. It's about 10 to the minus 35 meters, or about 0.0000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 The Planck length is 20 orders of magnitude meters across. The Planck length is 20 orders of magnitude smaller than a proton. If you scaled a proton up to the size of the observable universe, the Planck length would be about the size of a tree. At this scale, quantum effects on spacetime itself should become important. The smooth fabric of spacetime Einstein described should break down into something else, something grainy, something chaotic. Physicists call this quantum foam. It's the idea that if you could zoom in far enough, spacetime would look turbulent, bubbling with quantum fluctuations, constantly forming and dissolving tiny structures. But we have no direct way to probe these scales. The Planck length is so small that we can't build experiments to measure it. The energies required to probe Planck scale physics would be about 10 to the 19 giga-electron volts. The Large Hadron Collider, the most powerful particle accelerator ever built, reaches energies of about 14,000 giga-electron volts. To probe the Planck scale, you'd need an accelerator about 10,000 trillion times more powerful. That's far beyond anything we could possibly build with foreseeable technology. So we're stuck trying to figure out what happens at these scales, using pure theory, mathematics, and indirect reasoning. And there are several competing ideas, none of which we can test directly. One of the leading candidates is loop quantum gravity. This approach takes Einstein's equations and tries to quantize them directly. Instead of treating spacetime as a smooth continuum, loop quantum gravity says spacetime is made of discrete chunks connected in a network. Space is woven from loops, tiny loops of spacetime about a Planck length in size. These loops connect to form a network, and the geometry of spacetime emerges from how these loops are arranged and connected. In this picture, area and volume are quantized. You can't have an arbitrary area or volume. They come in discrete units, multiples of the Planck length squared or cubed. Spacetime has a minimum possible volume, and you can't divide it any smaller. This solves some problems. It suggests that singularities might not actually exist. At the center of a black hole, or at the Big Bang, instead of collapsing to an infinitely small point, matter would collapse to a minimum volume set by quantum effects. The singularity would be replaced by a quantum bounce or some other structure. But loop quantum gravity has problems. It's mathematically very complex, and it's hard to extract predictions that can be tested. It also hasn't been successfully unified with the other forces of nature or with quantum field theory, the framework that describes how particles interact. It's a quantum theory of gravity, but it's not clear how to incorporate the electromagnetic force, the weak nuclear force, or the strong nuclear force into the same framework. Another approach is string theory. String theory says that the fundamental objects in nature aren't point particles, but tiny vibrating strings. Different vibrations of these strings correspond to different particles. An electron is one vibration, a photon is another, a quark is another, and one particular vibration corresponds to the graviton, the hypothetical quantum particle that would carry the gravitational force. In string theory, space-time emerges from the interactions of these strings. The strings exist in a higher dimensional space, usually 10 or 11 dimensions rather than the 4 we experience, 3 of space and 1 of time. The extra dimensions are curled up so small we don't notice them, compactified at scales near the Planck length. And the geometry of space-time, the curvature we experience as gravity, comes from how the strings move and interact in this higher dimensional space. String theory is elegant in many ways. It naturally includes gravity. Unlike other attempts to quantize gravity that run into mathematical inconsistencies, string theory is mathematically consistent. It unifies all the forces. Electromagnetism, the weak nuclear force, the strong nuclear force, and gravity all emerge from the same framework, from strings vibrating in different ways. It has a rich mathematical structure that's deeply interconnected with advanced mathematics. Mathematicians have discovered new theorems and connections in pure mathematics by studying string theory. The theory emerged in the 1970s initially as an attempt to describe the strong nuclear force. That didn't work out. But physicists realized the theory naturally contained a description of gravity. In the 1980s and 90s, string theory experienced rapid development. Physicists discovered that there were actually 5 different versions of string theory, all mathematically consistent but apparently different. This was puzzling. If string theory was the fundamental theory of nature, there should only be one version. Then, in 1995, Edward Witten proposed that all 5 versions were actually different limits of a single more fundamental theory, which he called M theory. M theory works in 11 dimensions, 10 of space and 1 of time. The 5 string theories are different ways of looking at this same underlying theory. It was a major unification, suggesting that string theory might truly be unique. String theory has made concrete predictions about physics beyond the standard model. It predicts supersymmetry, a hypothetical symmetry that relates particles of different spins. For every known particle, there should be a supersymmetric partner. The electron would have a partner called the selectron, the quarks would have partners called squarks, photons would have partners called photinos. If supersymmetry exists, it would solve several problems in particle physics and provide a natural candidate for dark matter. But here's the problem. We've searched for supersymmetric particles extensively at the Large Hadron Collider and haven't found any. The LHC has probed energies up to about 14,000 giga-electron-volts, creating collisions energetic enough that supersymmetric particles should have been produced if they exist at accessible energies. But we haven't seen them. This doesn't rule out supersymmetry completely. The particles might be heavier than we can produce. But it's disappointing. String theory led us to expect supersymmetry at energies we could reach, and it's not there. String theory also has another serious problem. There are an enormous number of possible string theories, depending on how you curl up the extra dimensions. The extra 6 or 7 dimensions can be compactified in many different ways. Each way gives you a different 4-dimensional theory with different particles and forces. Current estimates suggest there might be 10 to the 500 different versions, maybe more. This is called the landscape problem. 10 to the 500 is an incomprehensibly large number. It's far more than the number of atoms in the observable universe, which is only about 10 to the 80. With 10 to the 500 possible string theories, how do we know which one describes our universe? There's no principle within string theory that selects one vacuum over another. Some physicists have argued that maybe all of these vacua are real, that each one describes a different universe in a vast multiverse. Our universe just happens to be one particular point in this landscape. We exist in this particular universe because the physical constants happen to allow stars, planets, and life to form. In other universes with different constants, life might not be possible, so there's no one there to observe them. This anthropic reasoning troubles many physicists. It seems to give up on the goal of explaining why the laws of physics have the specific form they do. Instead, it says the laws are essentially random, different in different universes, and we live in one of the rare universes where the laws allow life. It's not a satisfying explanation. It doesn't predict anything. It can't be tested. You can't observe other universes that are forever beyond our cosmic horizon. And there's an even more fundamental problem with string theory. It makes almost no testable predictions at energies we can reach with current or foreseeable technology. The natural scale of string theory is the Planck energy, about 10 to the 19 giga-electron volts. The LHC reaches energies of about 10 to the 4 giga-electron volts. To probe the Planck scale directly, we'd need an accelerator 10,000 trillion times more powerful than the LHC. Building such a machine is far beyond our technological capabilities. It might be beyond the capabilities of any civilization bound by the laws of physics as we understand them. Without testable predictions, how do we know string theory is right? It's mathematically beautiful. It's logically consistent. It unifies forces in an elegant way. But beauty and elegance aren't proof of truth. History is full of beautiful theories that turned out to be wrong. Physics requires experimental verification. We need to test theories against reality, and for string theory, that's incredibly difficult, maybe impossible. Some physicists argue that string theory has become more of a mathematical framework than a physical theory. It's produced important insights into mathematics and theoretical physics. It's given us tools for doing calculations in quantum field theory. It's revealed deep connections between different areas of physics and mathematics. But as a theory of fundamental reality, as a quantum theory of gravity that explains what space-time really is, it remains unproven. It might be a beautiful mathematical structure that has nothing to do with how the universe actually works. There's also a more radical idea that's gained traction in recent years. Maybe space-time isn't fundamental at all. Maybe space and time are emergent properties that arise from something deeper, something that doesn't look like space or time at all. This is the idea behind approaches like ER equals EPR, named after Einstein-Rosen bridges and Einstein-Podolsky-Rosen correlations. Here's the basic idea. Quantum mechanics allows for a strange phenomenon called entanglement. Two particles can be entangled such that measuring one instantly affects the other, no matter how far apart they are. This isn't communication faster than light because you can't control the outcome of your measurement. But it is a correlation that exists across space without anything traveling through the space between. In 1935, Einstein and two colleagues wrote a paper describing this phenomenon and arguing it showed quantum mechanics was incomplete. They thought the correlations must be explained by some hidden information the particles carried with them. But experiments have shown the correlations are real and can't be explained by hidden information. Entanglement is a genuine feature of quantum mechanics. Also in 1935, Einstein and Nathan Rosen wrote a paper about solutions to general relativity that contained wormholes. shortcuts through spacetime connecting distant regions. These became known as Einstein-Rosen bridges, but the wormholes in their solution were unstable. They'd collapse before anything could pass through them. In recent years, physicists have wondered if there might be a connection between entanglement and wormholes. The idea is summarized by the equation ER equals EPR, where ER stands for Einstein-Rosen bridges and EPR stands for the Einstein-Podolsky-Rosen entanglement. The suggestion is that when two particles are entangled, they're connected by a tiny wormhole, a thread of space-time linking them. If this is true, it would mean space-time itself is woven from entanglement. The connections between distant points in space, the geometry that we think of as space-time, would emerge from quantum correlations between particles. Space would be an illusion, a useful way of describing something more fundamental. Distance would emerge from the pattern of entanglement. This is speculative. It's not a complete theory, but it's motivated by serious theoretical work and by discoveries about the nature of black holes and entanglement. And it points to a possibility that's both exciting and unsettling. Everything we think we know about space and time might be wrong at a fundamental level. They might not be the basic building blocks of reality. They might be emergent, appearing only at large scales, like how the temperature and pressure of a gas emerge from the motion of individual molecules. The bottom line is this: we don't know what space-time is made of. We have equations that describe how it behaves. We can measure its curvature. We can detect waves moving through it. But the fundamental nature of the fabric itself remains a mystery. Also, in 1935, Einstein and Nathan Rosen wrote a paper about solutions to general relativity that contained wormholes, shortcuts through space-time connecting distant regions. These became known as Einstein-Rosen bridges. But the wormholes in their solution were unstable. They'd collapse before anything could pass through them. In recent years, physicists have wondered if there might be a connection between entanglement and wormholes. The idea is summarized by the equation ER equals EPR, where ER stands for Einstein-Rosen bridges and EPR stands for the Einstein-Podolsky-Rosen entanglement. The suggestion is that when two particles are entangled, they're connected by a tiny wormhole, a thread of space-time linking them. If this is true, it would mean space-time itself is woven from entanglement. The connections between distant points in space, the geometry that we think of as space-time, would emerge from quantum correlations between particles. Space would be an illusion, a useful way of describing something more fundamental. Distance would emerge from the pattern of entanglement. This is speculative. It's not a complete theory, but it's motivated by serious theoretical work and by discoveries about the nature of black holes and entanglement. And it points to a possibility that's both exciting and unsettling. Everything we think we know about space and time might be wrong at a fundamental level. They might not be the basic building blocks of reality. They might be emergent, appearing only at large scales, like how the temperature and pressure of a gas emerge from the motion of individual molecules. The bottom line is this: we don't know what space-time is made of. We have equations that describe how it behaves. We can measure its curvature. We can detect waves moving through it. But the fundamental nature of the fabric itself remains a mystery. Now let's turn to the second big question. What happened at the Big Bang? When we run the expansion of the universe backward in time using Einstein's equations, we inevitably reach a point where the entire universe was compressed into an infinitely small, infinitely dense singularity. This is called the Big Bang singularity. It's the beginning of time, the birth of space and matter and energy all at once. But calling it a singularity is another way of saying the equations break down. At the singularity, density becomes infinite, temperature becomes infinite, the curvature of space-time becomes infinite. Anything divided by zero or multiplied by infinity gives you nonsense. The mathematics stops working. And that means we don't actually know what happened. We have very good evidence for the Big Bang in a general sense. The universe is expanding. We can measure the expansion. We can see galaxies moving away from us in all directions. And when we measure the light from distant galaxies, we find that it's redshifted. The wavelengths are stretched because the space between us and those galaxies has been expanding while the light was traveling toward us. The farther away a galaxy is, the more its light is redshifted, which means the faster it's moving away from us. This relationship was discovered by Edwin Hubble in 1929, and it's one of the foundational observations of cosmology. If the universe is expanding now, it must have been smaller in the past. Run the clock backward, and everything gets closer together. Temperatures and densities increase. Eventually, you reach a point about 13.8 billion years ago when the universe was incredibly hot and dense. We call this the Big Bang, but that's a bit misleading. It wasn't an explosion in space. It was an expansion of space itself. We have other evidence too. In 1964, Arno Penzias and Robert Wilson discovered the cosmic microwave background radiation. They were working at Bell Labs in New Jersey, using a large horn antenna that had been built for satellite communications. They were trying to measure radio signals from the Milky Way, but they kept detecting an annoying background noise that wouldn't go away. No matter which direction they pointed the antenna, no matter what time of day or night, the noise was always there. At first, they thought it might be interference from New York City, but the signal was the same intensity from all directions. They thought it might be heat from the ground or the atmosphere, but the signal had the wrong spectrum for thermal emission from Earth. They thought it might be from bird droppings in the antenna, and they actually cleaned the antenna thoroughly, removing what they politely called white dielectric material. But the signal persisted. Finally, they learned that theoretical physicists at Princeton, just a few kilometers away, had predicted exactly such a signal. If the universe had started in a hot, dense state and expanded and cooled, there should be leftover radiation from that early hot phase. The radiation would have been stretched by the expansion of the universe from high-energy gamma rays down to microwave frequencies. And it should be coming from all directions uniformly because the early universe was nearly uniform everywhere. Penzias and Wilson had accidentally discovered proof of the Big Bang. The cosmic microwave background is light left over from when the universe was only about 380,000 years old. Before that time, the universe was so hot that atoms couldn't form. The temperature was over 3,000 Kelvin, or about 5,000 degrees Fahrenheit. At that temperature, electrons have enough energy to escape from atomic nuclei. Electrons and protons existed separately as a hot plasma. In this plasma state, light couldn't travel very far. Photons would constantly scatter off the free electrons, bouncing from electron to electron like a ball in a pinball machine. The universe was opaque, like being inside a thick fog or a cloud. You couldn't see through it because light was constantly being absorbed and re-emitted by the plasma. But as the universe expanded and cooled, eventually the temperature dropped below 3,000 Kelvin. At this point, electrons and protons could combine to form neutral hydrogen atoms. This happened rather suddenly across the entire universe, a transition called recombination. Suddenly, light could travel freely. The universe became transparent. Photons could stream through space without being scattered. Those photons have been traveling ever since. They've been stretched by the expansion of the universe from visible light with wavelengths of about 500 nanometers, or about 20 millionths of an inch, to microwave radiation with wavelengths of about 2 millimeters, or about 0.08 inches. The redshift factor is about 1,100. The universe has expanded by a factor of 1,100 since recombination. We can detect this radiation today coming from every direction in the sky. It's a nearly uniform glow with a temperature of about 2.725 Kelvin, just a few degrees above absolute zero. But it's not perfectly uniform. There are tiny variations, slight differences in temperature from one direction to another. Some regions are slightly warmer, about 2.7255 Kelvin. Some are slightly cooler, about 2.7245 Kelvin. The variations are only about 1 part in 100,000, incredibly small. But they're real and they're incredibly important. These variations are the seeds of structure in the universe. Regions that were slightly denser had slightly higher temperatures. These regions had slightly stronger gravity. Over billions of years, matter was pulled into these slightly denser regions by gravity. The dense regions became denser. The less dense regions became emptier. Over time, the tiny variations grew into the galaxies, galaxy clusters and superclusters we see today. Every galaxy, every star, every planet, including Earth, exists because of tiny quantum fluctuations in the early universe that left their imprint on the cosmic microwave background. We've mapped these temperature variations with incredible precision using satellites. The COBE satellite in the early 1990s made the first detections. The WMAP satellite from 2001 to 2010 mapped the sky in much higher resolution. The Planck satellite from 2009 to 2013 produced the most detailed map yet, measuring temperature variations across the entire sky with a resolution of about 5 arcminutes, about 1/6 the width of the full moon. From these maps, we can determine fundamental properties of the universe. The age, currently 13.8 billion years. The composition, about 5% normal matter, like atoms, about 27% dark matter, which we can't see directly but which has gravitational effects, and about 68% dark energy causing the expansion to accelerate. The geometry of space, which appears to be flat, meaning parallel lines stay parallel forever rather than converging or diverging. The rate of expansion, the Hubble constant, which tells us how fast galaxies are receding from each other. All of this from studying tiny temperature variations in ancient light. The cosmic microwave background is one of the most important pieces of evidence for the Big Bang. It's a snapshot of the universe when it was very young, and it matches the predictions of Big Bang cosmology in incredible detail. We can calculate what the temperature variations should look like based on our theories of how the early universe evolved, run computer simulations, and compare to observations. The match is extraordinarily good. Modern cosmology can explain the patterns we see to better than 1% precision. But when we try to understand the very beginning, the first moments, we run into problems. Einstein's equations predict a singularity, but singularities are places where the theory breaks down. At the Planck time, about 10 to the minus 43 seconds after the Big Bang, quantum effects on spacetime should become important. Below this time scale, general relativity can't be trusted. We need a quantum theory of gravity, and we don't have one. The best we can do is patch the problem with a theory called cosmic inflation. Inflation was proposed in the early 1980s by Alan Guth and others. The idea is that in the very early universe, there was a brief period when space expanded exponentially fast. In a tiny fraction of a second, the universe grew by a factor of at least 10 to the 26. A region smaller than a proton, inflated to the size of a grapefruit or larger. This solves several problems. It explains why the universe looks so uniform in all directions. Regions of space that are now billions of light years apart were once close enough to interact and come to the same temperature. It explains why space appears to be flat rather than curved. Any initial curvature would have been stretched out by the rapid expansion, just like the surface of a balloon looks flatter the more you inflate it. And it explains the origin of structure. Quantum fluctuations during inflation would have been stretched to cosmic scales, creating the tiny density variations we see in the cosmic microwave background. Inflation is supported by observations. The patterns in the cosmic microwave background match the predictions of inflation. But inflation doesn't solve the singularity problem. It just pushes it back. Inflation requires very specific initial conditions. You need a particular kind of energy field to drive the expansion. And you need the universe to start in a special state for inflation to work. Where did those conditions come from? We don't know. And if you trace inflation back far enough, you still reach a singularity where the equations break down. Some physicists have proposed alternatives. One idea is that the Big Bang wasn't the beginning. Maybe the universe bounced. Maybe it was contracting before the Big Bang and then bounced at a minimum size, transitioning from contraction to expansion. This would require quantum effects to stop the collapse before it reached a singularity, creating a quantum bounce. Loop quantum gravity suggests this might happen, but the mathematics is not yet fully worked out. Another idea is that the universe didn't begin from a singularity at all, but emerged from nothing through a quantum process. This gets into deep philosophical territory about what nothing means. In quantum mechanics, empty space isn't really empty. It's filled with quantum fluctuations, virtual particles popping in and out of existence. Some models suggest the universe could have emerged from a quantum fluctuation of the vacuum, a spontaneous creation event allowed by quantum mechanics. But all of these ideas are speculative. We don't have a complete theory that describes the origin of the universe. We don't know what happened at the Big Bang singularity, or whether there even was a singularity. The equations of general relativity point to a beginning, but they also tell us they can't be trusted at the very beginning. It's like a map that shows you how to get somewhere, but has a blank spot at the destination labeled, "Here be dragons." There's also the possibility of eternal inflation. Some versions of inflation theory suggest that once inflation starts, it never completely stops. Different regions of space stop inflating at different times, creating pocket universes, separate domains with their own physical properties. Our observable universe would be just one pocket in an eternally inflating multiverse. This is a bold idea, with profound implications, but it's also very hard to test. If other pocket universes are forever beyond our cosmic horizon, we can never observe them directly. The question of what happened at the Big Bang remains one of the deepest mysteries in physics. We know the universe had a beginning. We know it was once incredibly hot and dense. We know it's been expanding for about 13.8 billion years. But the very first moment, the nature of the beginning itself, is hidden behind a wall of ignorance. We need a quantum theory of gravity to go further, and we don't have one. Do black holes destroy information? The third big question brings us back to black holes and the information paradox. Do black holes destroy information? This might sound like an abstract philosophical question, but it cuts to the heart of how the universe works at the deepest level. Let me explain the problem more carefully. In quantum mechanics, the evolution of a quantum system is described by the Schrödinger equation. This equation is deterministic. If you know the quantum state of a system at one time, you can calculate its state at any other time, past or future. Information is conserved. The quantum state carries a complete description of the system, and that information never disappears. It might get scrambled, spread out among many particles in complex ways, but it's always there in principle. This is called unitarity, and it's a fundamental principle of quantum mechanics. Processes are reversible. If you know the final state perfectly, and you run the equations backward, you can recover the initial state. Information is never lost. But Hawking radiation seems to violate this. When a black hole evaporates, it emits thermal radiation that carries no information about what fell in. Thermal radiation is characterized only by temperature. It's random. If you collect all the Hawking radiation from an evaporated black hole, you can't reconstruct what went in. The information is gone. To make this concrete, imagine you write a book and throw it into a black hole. The book has information, the specific arrangement of words on each page, the precise positions of all the atoms that make up the paper and ink. In principle, if you knew the quantum state of the book perfectly, you could describe it with complete precision. Now the book crosses the event horizon and falls toward the singularity. From the outside, the black hole has gained a tiny bit of mass equal to the mass of the book. But you can't tell what fell in. The black hole doesn't carry any trace of the words on the pages. Now wait. The black hole slowly evaporates via Hawking radiation. After a very long time, much longer than the current age of the universe for a black hole of any significant size, the black hole disappears completely. All that's left is a cloud of photons and other particles, random thermal radiation. Can you reconstruct the book from this radiation? According to Hawking's calculation, no. The information is lost. The words are gone forever. This creates a paradox. Either quantum mechanics is wrong and information can be destroyed, or general relativity is wrong and black holes don't actually destroy information. Or both theories are incomplete and something else is going on that we don't understand. For decades, physicists debated this. Hawking argued that information really is lost, that quantum mechanics breaks down in extreme gravitational fields. Others, including Leonard Susskind and Gerard 't Hooft, argued that information must be preserved, that we just don't understand the mechanism. The debate was fierce. It became known as the Black Hole War. One key insight came from the holographic principle. This is the idea that all the information about what's inside a black hole is somehow encoded on its event horizon, the surface that marks the point of no return. The area of the event horizon is proportional to the black hole's entropy, a measure of how much information it contains. This suggested that the information isn't lost inside the black hole, but is stored on the surface in a scrambled form. The holographic principle was inspired by the work of Jacob Bekenstein and Stephen Hawking on black hole thermodynamics. They showed that black holes have entropy proportional to the area of their event horizon, not their volume. This is strange. For ordinary objects, entropy is proportional to volume. A bigger box can hold more information. But for black holes, it's the surface area that matters. This suggests that the information content of a region of space might be determined by its boundary rather than its interior. This idea was extended to a more general principle. The holographic principle says that all the information in a volume of space can be encoded on the boundary of that volume. The universe might be like a hologram, where the three-dimensional world we experience emerges from information encoded on a two-dimensional surface. String theory provides some support for this. In certain models, there's a mathematical correspondence between a theory of gravity in a higher dimensional space and a quantum field theory without gravity on the boundary of that space. This is called the ADS, divided by CFT correspondence, and it's one of the most important discoveries in theoretical physics in the past 30 years. It suggests that gravity and space-time might be emergent, arising from a more fundamental quantum theory that doesn't include space and time as basic ingredients. But even with the holographic principle, the information paradox wasn't fully resolved. The question remained: how exactly does the information get out of the black hole? Hawking radiation is thermal. It's random. How can it carry information? In recent years, there's been progress. The key breakthrough came from thinking more carefully about what happens to entanglement as a black hole evaporates. When Hawking radiation is emitted, the particles that escape are entangled with particles that fall into the black hole. This creates correlations between the inside and outside of the black hole. As the black hole evaporates, these correlations change in complex ways. In 2019 and 2020, a series of papers introduced the concept of quantum extremal surfaces and islands. The idea is that when you calculate the entropy of the Hawking radiation, you need to include contributions not just from the radiation itself, but also from a region inside the black hole, an island that's correlated with the radiation. As the black hole evaporates, this island grows. Eventually, it includes the entire interior of the black hole. At this point, the radiation carries all the information that fell in. Information is conserved after all. This led to a resolution of the Page curve problem. Don Page calculated in the 1990s that if information is conserved, the entropy of Hawking radiation should initially increase as the black hole evaporates, but then decrease back to zero as the last bits of the black hole disappear. This is because early in the evaporation, radiation is being emitted and carrying entropy away. But late in the evaporation, as more information escapes, the entropy should drop. The radiation becomes more and more correlated with what fell in. For decades, no one could explain how this Page curve could arise from the physics of black holes. But the recent work on islands shows that the Page curve emerges naturally when you calculate carefully. The entropy of the radiation follows exactly the curve Page predicted. Information is preserved. Does this mean the information paradox is solved? Most physicists think we're very close, but there are still some details to work out. The island calculation works in simplified models but hasn't been fully proven for realistic black holes in our four-dimensional universe. There are also deeper questions about what it means for information to be encoded in Hawking radiation in such a complex way. Can the information actually be extracted in practice? Or is it scrambled so thoroughly that it's effectively lost even if it's technically still there? But the progress is real. The black hole information paradox, which seemed like an unsolvable conflict between quantum mechanics and general relativity, is yielding to new ideas and new mathematics. And those new ideas point towards something profound. Space-time and gravity are not fundamental. They emerge from quantum entanglement. The fabric of space-time is woven from quantum correlations. And when we understand that connection fully, we'll have a quantum theory of gravity. So why does all this matter? Why should you care about whether space-time is made of loops or strings or entanglement? Why does it matter what happened at the Big Bang or whether black holes destroy information? These seem like abstract questions far removed from everyday life. But solving these mysteries could change everything. First, understanding what space-time is at the fundamental level would complete the picture of reality that physics has been building for centuries. Right now, we have two great theories. General relativity describes gravity and the large-scale structure of the universe. Quantum mechanics describes particles and forces at small scales. Both theories are extraordinarily successful. They've been tested countless times and have never failed. But they can't both be right in their current forms because they contradict each other. General relativity treats spacetime as smooth and continuous. Quantum mechanics says things are discrete and uncertain. General relativity is deterministic. If you know the state of the universe now, you can calculate its state at any other time. Quantum mechanics is probabilistic. You can only calculate the probability of different outcomes. These are fundamentally different worldviews, and they clash when you try to apply both to the same situation, like the interior of a black hole or the Big Bang. A quantum theory of gravity would unify these two pillars of physics. It would give us a single, consistent framework for understanding the universe at all scales, from the smallest particles to the largest structures. It would be the culmination of a quest that's been going on since the early 20th century. And it would almost certainly reveal new physics, new phenomena we haven't imagined yet. History suggests that major unifications in physics lead to technological revolutions. When Maxwell unified electricity and magnetism in the 1860s, it led to radio, television, telecommunications, and all of modern electronics. When quantum mechanics was developed in the early 20th century, it led to semiconductors, transistors, lasers, and computers. Every piece of modern technology relies on quantum mechanics. When Einstein developed relativity, it seemed abstract and impractical. But GPS satellites rely on relativistic corrections. Nuclear energy comes from Einstein's equation E equals mc squared, showing that mass and energy are equivalent. A quantum theory of gravity could lead to technologies we can't even imagine right now. If space-time is quantized, maybe we could manipulate it. Maybe we could create artificial gravity or control the flow of time. If wormholes can exist and be stabilized, maybe we could use them for travel or communication. If the multiverse is real and we could access other universes, the possibilities would be limitless. Now, these are all wild speculations. We have no idea if any of this is possible. Most physicists think it's probably not. The energy scales involved in manipulating space-time at the quantum level are so high that we might never be able to harness them practically. But the point is, we don't know. And history shows that understanding fundamental physics often leads to applications no one predicted. More importantly, understanding space-time would answer some of the deepest questions humans have ever asked. Where did the universe come from? What happened before the Big Bang? Will the universe end? What happens inside a black hole? Why does time flow in one direction? Why are there 3 dimensions of space and 1 of time? Why do the laws of physics have the form they do? These questions have fascinated humans for thousands of years. Every culture has origin myths, stories about how the world began. Every religion has grappled with the nature of time and existence. Philosophers have debated whether time is real or an illusion, whether the universe had a beginning or has always existed. For most of history, these questions were in the realm of philosophy and religion. Science couldn't address them. But now, we're close. We have mathematical frameworks. We have observational data. We have theoretical tools that might let us answer these questions definitively. A quantum theory of gravity could tell us what happened at the Big Bang. It could describe the interior of black holes. It could explain why time exists and why it flows forward. These aren't just scientific questions. They're existential questions about the nature of reality itself. There's also something philosophically profound about the fact that space-time might not be fundamental. We experience space and time as the stage on which everything happens. Objects exist in space. Events happen in time. Space and time seem like the most basic features of reality. The idea that they might be emergent, that they might arise from something more fundamental, challenges our deepest intuitions about existence. It's similar to how we now know that solid matter is mostly empty space. When you touch a table, you feel it as solid, but the atoms that make up the table are mostly empty space, with tiny nuclei and electrons. The solidity is an emergent property arising from electromagnetic forces between atoms. The table isn't fundamentally solid. Solidity is an illusion that emerges at large scales. If space-time is emergent, then distance and duration might be illusions in the same way. At the deepest level, there might not be any space or time. There might just be quantum information. Correlations between quantum bits and space and time emerge from the pattern of those correlations. This would be a radical shift in how we think about reality. There's also something philosophically profound about the fact that space-time might not be fundamental. We experience space and time as the stage on which everything happens. Objects exist in space. Events happen in time. Space and time seem like the most basic features of reality. The idea that they might be emergent, that they might arise from something more fundamental, challenges our deepest intuitions about existence. It's similar to how we now know that solid matter is mostly empty space. When you touch a table, you feel it as solid. But the atoms that make up the table are mostly empty space with tiny nuclei and electrons. The solidity is an emergent property arising from electromagnetic forces between atoms. The table isn't fundamentally solid. Solidity is an illusion that emerges at large scales. If space-time is emergent, then distance and duration might be illusions in the same way. At the deepest level, there might not be any space or time. There might just be quantum information, correlations between quantum bits, and space and time emerge from the pattern of those correlations. This would be a radical shift in how we think about reality. This raises fascinating questions about time travel. If space-time is a fabric that can be curved and warped, can it be curved so much that it loops back on itself, allowing travel to the past? Einstein's equations do allow solutions with closed time-like curves, paths through space-time that loop back to their starting point in time. These solutions describe things like rotating black holes and certain wormhole configurations. But closed time-like curves create paradoxes. The most famous is the grandfather paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. But if you're never born, you can't travel back in time to prevent their meeting. It's a logical contradiction. Some physicists have proposed ways around these paradoxes. Maybe the universe conspires to prevent paradoxes. Events arrange themselves so that any attempt to change the past fails. You try to prevent your grandfather from meeting your grandmother, but you fail. Maybe you're the one who introduces them. Maybe free will is an illusion in time travel scenarios and events are predetermined to be self-consistent. Or maybe time travel creates parallel timelines. When you travel to the past, you create a new branch of reality. In the original timeline, your grandparents met, and you were born. In the new timeline you created, they don't meet. But that doesn't affect your existence, because you came from the original timeline. This is the many worlds interpretation applied to time travel. Or maybe time travel to the past is simply impossible. Maybe the laws of physics prevent it at a fundamental level. Stephen Hawking proposed a chronology protection conjecture. He suggested that the laws of physics conspire to prevent closed time-like curves from forming. Whenever you try to create a time machine, quantum effects become important and destroy the path before it can close. We don't know which of these possibilities is correct. We don't have a complete theory of quantum gravity that could tell us whether time travel is possible. But the fact that Einstein's equations allow closed time-like curves suggests that space-time is stranger than we imagine. Time might not flow in one direction as inexorably as we think. The past, present, and future might not be as separate as they seem. Understanding this could change not just physics, but how we think about existence itself. It could shift our philosophical understanding of what it means for something to exist, to happen, to be real. These are the kinds of questions that sit at the boundary between science and philosophy, and they're questions that a quantum theory of gravity might actually help us answer. Understanding this could change not just physics, but how we think about existence itself. It could shift our philosophical understanding of what it means for something to exist, to happen, to be real. These are the kinds of questions that sit at the boundary between science and philosophy, and they're questions that a quantum theory of gravity might actually help us answer. There's also the search for life and intelligence elsewhere in the universe. If we understand space-time better, if we know whether wormholes or warp drives are possible, it changes what we expect for the future of civilization. If faster-than-light travel is impossible, then civilizations are confined to their home star systems, or at best a few nearby stars. The universe would be full of isolated civilizations, each developing alone. But if shortcuts through space-time are possible, then the galaxy could be connected. Civilizations could meet, communicate, trade ideas. We don't know which scenario is correct. The physics suggests that faster-than-light travel is impossible, but we can't be certain until we have a complete theory of quantum gravity. There might be loopholes. There might be ways to manipulate space-time that we haven't discovered yet. Understanding space-time at the deepest level would tell us whether these possibilities exist, or whether we're forever limited by the speed of light. And finally, there's the simple beauty of understanding. Humans have always looked up at the sky and wondered. We've built observatories, telescopes, particle accelerators, gravitational wave detectors, all to understand the universe. We've sent probes to other planets. We've photographed black holes. We've detected the cosmic microwave background. All of this is driven by curiosity, by the desire to know. The mystery of space-time is one of the last great frontiers. It's the place where our two best theories collide. It's the doorway to understanding the beginning of the universe, the fate of matter in black holes, and possibly the nature of reality itself. Solving it would be one of the greatest intellectual achievements in human history. It would be a triumph comparable to Newton's laws of motion, Darwin's theory of evolution, or the discovery of DNA. We're living in a special time. We're the first generation to have the tools to probe these questions seriously. We have gravitational wave detectors that can measure ripples in space-time. We have telescopes that can photograph black holes. We have particle accelerators that can create conditions similar to the early universe. We have mathematical frameworks like string theory and loop quantum gravity that might describe quantum space-time. And we have brilliant physicists all over the world working on these problems. We might be close to a breakthrough, or we might be decades or centuries away. Science doesn't progress on a schedule. Sometimes the breakthrough comes quickly. Sometimes it takes generations. But the fact that we're asking these questions, that we're seriously trying to understand the fundamental nature of space and time, is itself remarkable. We're pushing the boundaries of human knowledge. We're trying to understand the universe at its deepest level. And even if we don't solve the mystery in our lifetimes, the journey itself is worthwhile. So let's come back to where we started. Spacetime, Einstein's idea, the foundation of modern physics. The framework that describes gravity, the expansion of the universe, black holes, gravitational waves, and the Big Bang. An idea that's been tested thousands of times and has never failed. An idea we use every single day in GPS satellites, in our understanding of the cosmos, in the technology that surrounds us. And yet, the fundamental mystery remains. We don't know what it's made of. We don't know if it's fundamental or emergent. We don't know what happened at the Big Bang when the equations predict a singularity where physics breaks down. We don't fully understand whether black holes preserve information or destroy it, though we're getting close to an answer. We have equations that describe its behavior, but we lack a complete theory that explains its true nature. This isn't a failure. This is where we are. This is the frontier of human knowledge. Every great idea in science eventually reaches a boundary where it can't go further without something new. Newton's laws reached that boundary when scientists started measuring the speed of light and the orbit of Mercury. Quantum mechanics and relativity reached that boundary when scientists started thinking about black holes and the Big Bang. And now we're at the boundary again. We're at the place where the smooth space-time of Einstein's theory meets the quantum world of particles and uncertainty. Somewhere beyond that boundary is the answer. A quantum theory of gravity, a description of what space-time is at the Planck scale, an understanding of what happened at the beginning of the universe. The resolution of the information paradox. Maybe a unified theory that describes all forces and particles. Maybe a multiverse. Maybe something we haven't imagined yet. The physicists working on these problems today are standing at the edge of a cliff, looking out into the unknown. They're using mathematics and creativity and centuries of accumulated knowledge to build bridges across the gap. Some of those bridges will fail. Some will lead nowhere, but one of them might reach the other side. And when it does, when someone finally figures out what space-time really is, it will change everything. So the next time you use GPS, or look at a photograph of a black hole, or think about the Big Bang, remember this. You're looking at one of the deepest mysteries in all of science. You're seeing the evidence of something we use but don't fully understand. An idea that works perfectly in practice but remains mysterious in principle. Space-time is real. We can measure it. We can photograph it. We can detect waves moving through it. But we don't know what it is. And that's okay. That's where the adventure begins. That's where science happens. Not in the answers we've already found, but in the questions we're still trying to answer. Einstein gave us the idea of space-time over 100 years ago. It revolutionized physics. It explained gravity. It predicted black holes and gravitational waves and the expansion of the universe. It's been one of the most successful theories in the history of science. But Einstein himself would probably be the first to admit that it's not the end of the story. It's not the final answer. It's a step along the way. A beautiful, elegant, powerful step, but still just a step. The final answer is waiting. It's out there in the mathematics, in the experiments, in the observations yet to be made. Someone will find it. Maybe in our lifetimes. Maybe in the next generation. Maybe centuries from now. But it's there. And when we find it, we'll look back at this time. This moment when we knew that space-time exists but didn't know what it was. And we'll see it as the turning point. The moment just before everything changed. Thank you for joining me on this journey through space-time and its mysteries. If you found this exploration valuable, a like or subscribe would mean a lot. It helps me continue making these deep dives into the cosmos. And remember, the universe is full of mysteries waiting to be solved. Space-time is just one of them, but it might be the most important one. Good night. And may you never look at empty space the same way again.